Hello everyone. In this course, we'll talk about circuit design and spice simulations. So let's try to break up into two parts. One is the circuit design and other is spice simulation. So when we talk about circuit design, it's basically the gates. We have these logic gates, the AND, OR, NOR, inverter, buffer, and all these logic gates are made up of PMOS and NMOS transistors connected in a very particular fashion. And once they are connected in that fashion, they perform the required functionality of that particular respective gate. That's basically circuit design. And I have a small example of this one. So for example, this is an inverter. You have this PMOS transistor, you have this NMOS transistor. The drain of the NMOS and the drain of the PMOS are tied together. The gates of these both transistors are tied together. And basically this particular connection fashion of the PMOS and NMOS transistor gives you the functionality of an inverter. Similarly, you will have a bunch of PMOS at the top, you will have a bunch of NMOS at the bottom, which might give you a functionality of a NAND gate or an OR gate or an AND gate or any kinds of gates. So basically, in circuit design, we'll try to understand what kind of PMOS transistors and what kind of NMOS transistor, when connected in a certain fashion, gives you the required functionality. Okay, that's about circuit design and spice simulations. So now this particular circuit has to be fed in with some waveforms to identify the output characteristics. For example, you take this PMOS transistor and you take this NMOS transistor, the characteristics of them will look something like this. So these curves, which I will be talking in some time from now, these curves are basically the characteristics curves of NMOS. They describe NMOS transistors. Okay, and the curves that you see over here, an inverted form of these curves describes the PMOS transistor. Okay, and then you feed on these two, you basically simulate this transistor using spice, and you get waveform something like this. And this particular waveform will actually decide the delay of this particular cell. So based on the value of the delay, you can actually tune the W and L ratio of this particular transistor. So this transistor will comes up with some W and with some width and with some length. And W by L ratio is the factor that decides the value of this currents. And the value of this currents will eventually decide the waveform shape that you see over here, and these shapes decide the delays of this particular cell. So if you want to tune the delay, how do you tune the W by L ratio? That's basically can be obtained using spice simulations. Okay, so but the question is, why do we even want to do all this? Why do we want to do spice in the real world? Because if you look into a VLSI, into VLSI a factory, you might be doing a physical design flow, you might be doing clock tree synthesis, you might be doing crosstalk. There is nowhere the mention of the word spice. So why do we need spice? And the answer is, this is a very important thing that needs to be done while doing a clock tree or while doing physical design flow. So let me try to answer, why do we even want to need spice? So basically, whatever we have been doing till now about the clock tree, about timing, about crosstalk, they are on built on something called as spice. If this would not have been there, there would not have been won't have been any term called as delays. And if you don't have delays, the clock tree, crosstalk, physical design flow doesn't make any sense. So let's try to answer, why do we even need to do spice? Okay, so let's take an example over here. For example, this is a buffer. You have this buffer of type 1, you have this buffer of type 2. Okay, and I've given some specifications over here. So this is a snippet that I've taken from one of my previous course on clock tree synthesis. Okay, and there is some specifications of this particular buffer. We have taken the output load of at this particular node as 60 femtofarads. Okay, we have taken the output load at this point as 50 femtofarads, it's mentioned over here. And we have taken the output load at this point as 50 femtofarads. So we have assumed some values over here, and these values do come with some calculations, which I have explained in my clock tree synthesis course. You might want to have a look into that course. So these values come after some precaution calculations over here. So next what we'll do is we'll try to create a delay table for this particular cell. So if you want to calculate the delay of this particular cell, you don't run spice every time. You already have a ready-made delay table, and this delay table consists of the input slew and output load. So it's a combination of input slew and output load, and whatever is the value of input slew and output load, that particular intersection value is being considered as the delay. So now let's take an example over here. So values inside this particular table will be all delay values. So it basically says that if this particular buffer has got an input slew of, let's say, 80 picosecond and has got an output load of, let's say, 70 femtofarads, the delay of this particular cell will be x22. Okay, for example, there is one more, let's take one more example. So this is a delay table for the buffer 2. So this is a buffer of type 2, and it has got a similar delay table but with different values, because this buffer might be made of some different PMOS and NMOS transistors. This buffer might be made of some different PMOS and NMOS transistors, and in reality every PMOS and NMOS transistor differentiates from its nearby transistors. Basically, this could be of a lower drive strength, and this could be of a higher drive strength. Okay, so let's say this, so that's the reason this will have a different delay values. So this is the delay table for the buffer of type 2. So this says that of the same, let's say, we'll take same example. If this buffer sees an input slew of 80 picosecond and an output capacitance of 110 femtofarads, the delay will be y24. And over here the delay will be x24 for the same values of input slew and output load. So that's basically differentiates between CBUF1 and CBUF2. Now how these two are getting differentiates, that's basically circuit design. That's basically circuit design part of this particular course that we'll be talking about. So this CBUF1 we will be having a different W/L ratio. This CBUF2 will be having some different W/L ratio. Maybe this one has got a smaller width, this one has got a bigger width, and so on. So that's basically circuit design that will be answering the answer to this differentiates the answer to different kinds of buffers is basically circuit design. Okay, now let's come to the delay values. First of all, let's take an example that will make more sense over here. So let's say we have a input slew of 40 picosecond. Okay, that marks this particular row of the delay table. Since it's of type 1, this is this particular row of this delay table. And let's say an output capacitance, we already know at node A the output total cap is 60 femtofarads, but 60 femtofarads, we don't have the column for 60 femtofarad, so it will lie somewhere over here. Okay, so x9 and x10 are the most probable values, and somewhere between x9 and x10 lies your delay of CBUF1. That basically value is being interpolated through some equations, and then you get this value, and x9 dash is the delay of CBUF1. Okay, similarly, let's take another example where you have the where you have the buffer type 2. So let's say the input slew of this particular buffer is 60 picosecond. So that basically locks in this particular row of the delay table from CBUF2. Okay, and the output capacitance at this point is, let's say, 50 femtofarads, so that locks this particular column of the output load. Now the intersection of this input slew and output load is y15, which becomes the delay of this particular cell. Okay, so now with that said, we have now the delay values. Now the questions that we have to ask is, the first question is, where does this delay of the cell actually comes from? We know that they come from this particular table, but where does this table actually comes from? What is the source of this particular table? Okay, that's the first question that generally hits the mind, because these are not coming from some numbers. These are not just some numbers. There has been some characterization done behind getting these numbers. So what is those characterization? Where are these numbers actually coming from? In fact, where are these numbers coming from, and why are these two numbers different? Because this is of a different type, this is of a different type, which we will be answering in a circuit design, from a circuit design point of view. And where are these delays coming from, that will be answering from a SPICE simulation point of view. Okay, the second question to ask is, we have learned about the delay models, but are these delay models accurate? Are these accurate enough to be used in our circuits? Because finally this chip will go on to a tape out, and that will go into a product, so the product should function properly. So we have to understand whether these models are actually accurate, and that how we'll be doing, how we'll be getting it. We have to supply same input slew and same output load in a SPICE simulation, and then get the delay value from SPICE and match it whether that delay value matches with this delay value. Okay, so that's the second question that we need to answer, and I'll be talking about how do we do that in reality. Third question is, how do we even verify whether what you are doing in static timing analysis is correct or not? So basically the delay values, the slag values, whatever you see in your static timing analysis, how do you verify whether those values we can trust those values? How do we even identify that? Because these are just tables, and there are some equations that is running behind it to extract the values from these tables. But the source of this table is very important, and the source of this table comes from SPICE, comes from circuit design. And basically SPICE simulations involves characterizing the NMOS and PMOS transistor into detail, basically any CMOS logic into detail. Okay, so that will involve us to first start with what is an NMOS transistor. So what we'll do is, since I'm already running out of time, we'll start with the NMOS transistor, which is the first basic transistor that we have to learn, where we'll try to derive some characteristics of NMOS transistor, the voltage and the current characteristics that we just shown in couple of minutes back. And then we'll try to identify the delay of NMOS and PMOS when connected in a different fashion. So let's try to do all this in the next video. Thank you.